Good morning, everybody. Bonjour. So I'm Walter Koop, and I've been proposed by the organizers, to whom I would gladly thank for the task, to tell you about liquids and mainly time correlation function, structure, etc. And so I'm from the University of Montpellier too. And before you start to talk to your neighbor, where on earth is this? So I give you a brief zoom onto Central Europe. This is France. Montpellier is down here on the coast in the south of France. So little bit of what I'm going to talk about. So in the first part, I'm going to talk about liquids. In the second part, about the theory of the glass transition. So first of all, I would to justify why on earth I want to talk about liquids. And once I hope to have convinced you that it's interesting, so I hope you will listen to on how a liquid can be characterized from the structural point of view. So I will talk about radial distribution functions, static structure factor, etc. And then go into something which is a little bit more interesting about the characterization of the dynamics of liquids. And here concepts, relevant concepts will be mean square displacement, diffusion constant, Van Hove function, intermediate scattering function, viscosity, susceptibility, Stokes-Einstein relation. So Austin Angel and Gilles Darjus have already mentioned many of these concepts yesterday. And so I got the task, explain everything as simple as possible so that everybody is on the same level. I understand that many of you will say, okay, we know, why are we wasting our time and have to get up early? But it's really, since it's a really mixed audience, I was assigned the task that everybody should at least know a certain, have a certain level on these things. Okay, so please be patient on this. Now, why discuss liquids on this school? Because in the title it's glass forming systems and glasses and not liquids. But Gilles showed already yesterday this plot here that comes from Austin 15 years ago, which is basically the temperature. Here we have a temperature action, here a pressure axis, and it's all these blobs here are various possibilities how to form a glass. So usually what you're thinking is a glass where you cool down and then it's getting sluggish, falls out of equilibrium, and that's what a glass is about. But what you also can do is to take, for example, a nice crystal and you start to compress it. So you're at low temperature, so you're on this corner here, you're at low temperature, and then you start to increase the pressure, and the crystal will yield a little bit, become smaller and smaller, but at some time it will just break apart, within your animal cell, for example, and then it will start to form a glass. This glass perhaps is not stable in the sense that if you take away the pressure, it's not that clear what's happening, depends on the system, but it's certainly one possibility to produce a glass. Another thing is you take, again, a crystal and you put it in a nuclear reactor, for example, so the nucleons or the neutrons are bombing on the cores of the atoms, and they will displace them in a random way. And again, after a few days, you take out your nice crystal and it has been transformed into a glass. So again, so this glass has never seen a high temperature, and nevertheless, it is really amorphous. It's a glass. It's no longer a crystalline structure. This is also the remark yesterday where about this glass transition, fictive temperature, this difference. So you see that actually you can produce glasses that have never seen a high temperature phase. And so it's clear, and so there are all the possibilities. I don't want to go through all of them, so ask the author of the slide to explain everything to you. He's going to pay your beer and tell you a lot about it. But the main route, nevertheless, is that usually is that you go to the high temperature phase. There, it's a liquid, it's in equilibrium, quasi-equilibrium. You can use statistical mechanics, and then you slowly cool down your sample. You fall out of equilibrium, and you get the glass. So this high temperature route, this is still from the theoretical and from the practical point of view, the main thing how to produce a glass, and that's why I'm going to tell you about liquids. Now, how can you characterize liquids? I had h bar, so it will be equal to 0. For most glass physics, it's not important except if you are looking at specific heat at low temperatures. So you are talking about n identical classical particles, and I want to know the r sub j, the position of a particle at a given time t. Now, the radial distribution function is defined in this way here. So basically, you look at all pairs of particles in your system. You look what system distance do they have. If you find, and you make a histogram, this is the Dirac delta function here of that distance, and you look at the distribution of these distances. Here you have a normalization factor that is usual, and this function here, so which is the histogram on the vectorial distance between any two particles. This is called the radial distribution function. So the brackets here, these are just the thermal average. Usually if you have a very big system, you don't need it as long as you are in equilibrium. Now here please note these are really a vector quantity. That's why it's the radial distribution function. However, if for most liquids they are isotropic, that is to say the properties do not depend whether you look in this direction, this direction, this direction, and therefore you can integrate this histogram over the direction, and the only thing that stays is then radial dependence, and therefore you can replace the vector argument here by its modulus r without not in boldface, and you are looking at what is called the pair correlation function. And here you throw in a factor 4 pi r squared, which is nothing else than the phase space volume that you pick up because you have integrated over a shell over a sphere of radius r. Okay. So I will discuss the shape of this function in a moment. Normally in experiment this quantity is not directly accessible. However, if you look at superatoms, that is to say colloidal systems, you can have a look at the position of the atom with a confocal microscope, and very nice work also done here in Bangalore on this. And so colloidal system, if the particles are not too small, let's say a few hundred nanometers, then you can see them within the microscope, and then actually you can calculate this quantity. From a theoretical point of view, this is indeed a very important quantity because it gives you the relative position of any two particles, and of course you also can measure it and study it in computer simulations. Now, from a theoretical point of view, there are theories which are called integral theories. Key words are Perkusiewicz, hyperneto chain equations, etc. That give you approximate schemes how to calculate this quantity. So there is, give me the potential and I can calculate this quantity here. How are the distances between particles distributed? Okay. Parenthesis, what I forgot at the moment, please interrupt me at any time to ask questions. I think it shows me that you have not fallen asleep yet. So, pair correlation function. So this is the definition I just wrote, and this here is an example from a computer simulation of a simple liquid. In this case, it's a binary Lennard-Jones mixture, which shows you how the G of R depends on the distance here. So the red curve is the G of R. So what you see is that for small distances, it is 0, and it's reasonable because this function here tells you what is the probability to find a certain distance between two particles. And the probability is very small if the distance is small because the particle cannot sit on top of each other, because there is a hardcore repulsion due to the Pauli principle between the atoms. So typically for a dense liquid here, this is exponentially small, and then you find the first peak and then some additional smaller peaks that are quickly damped with increasing distance. So what is the physical meaning of this peak? So if you have a tagged particle, the red one here, that is sitting here at the origin, so this peak here corresponds to the first shell here of the surrounding particles. and then this first shell has a second shell. This gives rise to the second peak, etc. So this are these wobblings here. So that's something that is, with your hand, you understand quite easily. Now, the G of R is useful to characterize the structure on very short distances. First nearest neighbor shell, the second nearest neighbor shell. Now, if you are interested in larger distances, this G of R is no longer interesting, because if you look at it, it basically becomes just flat. If there is a superstructure at larger distances, you don't see it anymore. So, one way to understand the structure on larger scale is to look at the so-called static structure factor, which is defined here. So you have here an additional quantity instead of space of distance. You have a wave vector. So you are now in reciprocal space. And this here is the definition of the static structure factor. So again, you take the particle distance, you multiply it with the wave vector, multiply with minus I exponential, and you take the thermal average of this quantity. Now, if you are using this definition, and you recall the definition of the radial distribution function, it's easy to show that there is a simple relation between the static structure factor and the radial distribution function, because it's nothing else than the space Fourier transform of this quantity. So technically, if you know the G of R, you can calculate the S of Q. Okay? And this is the relation between it. Now, for isotropic systems, so again, here this was for a vector quantity Q. If you have an isotropic system, the static structure factor does not depend on the direction, and therefore, again, you can make a circular or a spherical average, and you end up with this expression here. So again, if you know the pair distribution function, then you can calculate directly the static structure factor. Okay? Yes?
Just to be clear, since the two contain exactly the same information,
yes.
what you mean is that the GFR is not a sensitive indicator of structure that may exist at long distance. You said it's not useful.
Well, it's not, of course it's useful, but if you look in practice, if you have a system that has some sort of short-range order and some sort of long-range order, you will see the short-range order in G of R, but you will never see the long-range order, or it's really very, very hard. Of course, mathematically it must be there somewhere, but it's so hidden that it's usually hidden in the noise. Okay, but you're right. Now, so mathematically, there is excuse me, the relation between the static structure factor and the G of R via the Fourier transform, and therefore it's evident, if you recall basic mathematics, that there must also be a relation between the G of R and the S of Q, and indeed the G of R is just the Fourier transform, apart from some prefactors, of S of Q, minus 1, okay? And so technically, if you know the S of Q, you also can calculate the G of R. And I will show on the next slide that the S of Q can indeed be measured in real experiment, Newton or X-ray scattering experiment. And therefore, the experimentalists, well, they have access to this quantity, but interpreting S of Q is much harder than interpreting G of R. And therefore, the experimentalists, they love to take this expression or a similar one and to calculate the G of R. And my warning is, don't believe this result. I think 80% of the people are cheating on this because, well, I mean, there is a mathematical transformation, fine, but in the experiment, you cannot measure S of Q up to very, very high wave vector, that is to say very high Qs. Even if you have very good data, usually this Fourier transform is highly unstable, and you get out something that looks good, but is likely to be wrong. So if you want to look at the G of R, let's say on a 5% level, normally I don't believe it. You get more or less the right features, but I think the experimentalists, they rather should stick with the S of Q. Of course, everybody's getting mad at me now, but this is... no. Okay. He claims that it's possible, but you see how they are resistant. Huh? There are very few people that, I mean, it is possible, of course, but usually, especially with neutrons, it's really very, very hard. And there are additional problems that I will discuss a little bit later. So take care of this one. Now, how does this function look like? So you can measure it in Newton X-ray scattering experiments. So what's happening is that you come in, let's say, with the neutrons that have a certain wave factor, since they have a certain energy, and they scatter off of the sample. They come out with another wave factor. You take the difference of this wave factor, this is your Q, and you put up the detector at the end of the beamline, and you see how does the signal, scattering signal, depend on this wave factor Q, and this basically, apart from certain prefactors, gives you the S of Q. And these are again the same. It's the same Binary-Lennard-Jones mixer, just for the sake because I had the data in my hand. And so you see how this function looks like. So again, there is a strong peak here, which is basically 2 pi over the position of this, the location of this peak here, and then there are additional wiggles that go out to larger wave vectors. So one thing that you should note, even if you probably are not able to see it, is that if you go to small wave vectors here, the S of Q does not go to 0, it goes to a finite value, and this finite value here is related to the isothermal compressibility, kappa T, which is defined here. So that tells you whether the sample is soft or hard. So if the value here is small, it's a very hard sample. If it's very soft, it's a very soft sample. Okay, so that's the interest in the S of Q. Now, most systems are not one component, because one component system is relatively simple. They are multi-component. That's where things get a little bit more interesting, but also more complicated. So consider a system with new components. So you have the number of particles n1, n2, and the sum of this is n. Okay, and so what you can do now is to generalize the radial distribution function by considering now pairs of a certain type. So let's say if you have particles of type 1, 2, and 3, you can look only at pairs between particles of type 1, type 1, type 1, type 1, and you take the thermal average of these distances, and you get this partial radial distribution function G alpha alpha, where alpha runs from 1 to nu. But then you also can look at the particles of type 1 and see where are the particles of type 2, 2, 2, 2, and you look at the statistic of these distances. So this is the G alpha beta. Okay, and correspondingly, you also can define what is called the partial structure factor, which is just the Fourier transform of this quantity here, that look again at the Fourier transform of the G alpha alpha. And so this gives you a S alpha alpha, which is defined in this way, with the F alpha alpha equal to 1. And you can look at the cross correlation between different type of particles. So this is for the case that alpha is not equal to beta. And in that case, the F is 1/2. Okay? And so again, this is a quantity that you can study in experiment in principle. However, what you do in reality, so you have a multi-component sample, you put it in your sample holder, you do your scattering experiment. What you are measuring, this is exact, is a linear combination of these partial structure factors. So here alpha and beta run from 1 to nu. So if so you have nu square terms here because you have nu square partial structure factors. And so here you have a funny prefactor that comes from the normalization. So that's what is accessible in a Newton scattering experiment. Now the prefactor B alpha and B beta has something to do with the Newton scattering cross-section. That is to say, the neutron, it does not see really the whole atom, it just sees the nucleus. And whether or not it scatters depends on the properties of this nucleus, that is to say, on the material or the element that you're considering. So the B alpha, these are values, I don't want to say they are random numbers, but they are values that have to be measured, and they have been measured, they are published, and you type Newton-Scattering cross-section on Google, and then you find, I know, on ISIS, I think, there are nice sites where you find tables on with what are these values. So what the experimentalists measure is this quantity here, and not necessarily the partial structure factor. Now, so this is bad news, because instead of measuring nu square partial structure factor, they just get a weighted sum of these quantities. However, the good news is that these Newton-Scattering cross-sections, they depend on the isotope. And so what you can do, for example, you take the same sample, but you replace one of the elements with another isotope of the same element. And therefore, you have changed the B alpha of that quantity. And now if you think a little bit, if you do enough substitution, if you have enough isotopes of the different elements, if you are doing nu square experiments, then indeed you are able to get the partial structure factor, because this is just a linear problem. Okay? But you see, this is doable if nu is 2, because there you have 2 elements, so you need to measure 3 partial structure factor. So that's still doable. But if you have a 5-component system, it's evident that's no longer possible, because nobody's going to give you the beam time except if you're the boss of the institution, and then you can get it. But in fact, there are a few very nice experiments by Phil Salmon, for example, in which he measured for SiO2, germanium dioxide, the partial structure factors, and therefore this information is much richer than just the average neutron scattering structure factor. Okay, so this is neutron. Now, if you're looking at X-ray diffraction, the situation is very similar, except that this constant B alpha, the Newton scattering cross-section, have to be replaced by functions that depend on the wave factor. So that's what I call here X alpha of Q. So this function depends on the element that you're considering, silicon, or oxygen, or whatever, and also on the wave factor considered. And again, these functions, they are published on the web, so you just download them, and then you can extract this information here. So again, if you are just doing standard X-ray diffraction, then the only thing that is accessible is this weighted sum here. And of course, unfortunately, the X-ray, it's not seeing the nucleons, it's seeing the electrons. Okay? And you cannot change the electrons of an element. Therefore, in X-ray diffraction, you cannot play this game with the isotopes, that is to say, you measure it once and that's what you get. End of story. So from this point of view, neutrons are indeed more interesting than X-rays, even if they are a factor now 10 to the 10 cheaper probably than the neutrons. Okay. Last thing, so these are multi-component system, but realize that if you have just a one-component system, so nu equal 1, all these factors here, they cancel, and indeed you find that the neutron scattering function is equal to the S static factor equal to the S of Q. So if you have just a one-component system, whatever you do, as long as you do it correctly, neutron or X-ray, it gives you the same answer. So this is the good news for one-component system. So how do this look like, this multi-component system?
Neutron scattering, say quickly why the Q dependence is not there. Why is there no Q dependence in the cross-section of neutron?
It's so small. I mean, the nucleus is a point basically, and that technically there must be one, but I mean you approximate it with this Fermi potential thing that is so small that you can forget about it. Is this correct?
Yeah.
Thank you.
If you go to pound to US axis, so then you see.
Okay.
The Q dependence in X-ray comes from the extended charge distribution, which goes into the form factor. When
because you have a charge distribution, so you will correspondingly, if you do a Fourier transform, you will also get a Q dependence. Whereas, as he mentioned correctly, that for nuclear scattering is effectively a point object, so you don't have the Q dependence in that.
Okay. So how? Okay. So how does real life look like? So I recall here the equation for the Newton scattering function, and so this is again, it's a simulation. It's not because it's better than the experiment. It's just I had it, and it's simpler to show my point. Sorry about this. So simulation of SiO2, so a binary system, and here it's at different temperature, but so the static structure factor between the silicon atoms. And so just look at the lowest temperatures, that's the black curve here, that is the most peak, or where it has peaks that have the highest values. So here, of course, since you have a binary system, you have 3 partial structure factor, I don't show the other 2s, and you can use this formula to calculate the Newton scattering section. And the blue line here is what you get out if you use this formula and the corresponding 2 other static structure factors. So the message is that here you have a first smaller peak, which corresponds to the distance between tetrahedra. This is another peak here, which corresponds to a smaller distance. But this peak is higher than that one, okay? So that's the truth. And then you let it run through this machinery, and the outcome is that this first peak here is more pronounced than the second peak here, okay? And it's just because you have taken this linear combination, and especially in the case of SiO2, the SiO static structure factor here, for example, is negative, and that's why this peak here is suppressed, okay? So you see that by looking at something like this, it's hard to infer what are the real positions between, let's say, silicon atoms, or between oxygen atoms. Because that's all what you get, and then you have to make some guesswork. Does this peak here is the superposition of this peak plus a little bit of that, etc. What I also insist, because sometimes one still hears and reads this nonsense, is that, for example, the width of this peak here has something to do with the size of correlated regions or stuff like this. This is really rubbish, because this peak here is the superposition of several peaks that are positive and negative, and therefore you cannot extract the correlation lengths from the width of this peak. Not possible. If you have a one-component system, it is possible, it's exact. If you have a multi-component system, it's no longer possible. So this here is a relatively simple, just a binary system, silica. Now, if you put in a little bit of sodium in the system, here things really can get complicated. So again, here I'm showing, so it's a computer simulation again. Sodium disilicate, this is the partial structure for oxygen, and here for sodium. What you see here is that around 1 inverse angstrom, you see a quite nice peak in the sodium correlation. You let it run through this machinery, so you have 6 partial structure factor. This very nice peak here hardly shows up here. If you have a problem with your resolution, you do not see this peak anymore. So you see how dangerous, in quote unquote, this information is. You might have a peak, that is to say a real structure in your sample, and you do not see it because by stupid cancellation effect or unfortunate cancellation effect, this feature gets basically smeared out and you don't see it anymore in the data that you're measuring. Okay?
So instead of looking at the total structure factor, depending on what type of quantities you are interested in, one can define as various different types of combinations. For example, concentration.
Correct. Yes.
Density. So that will give much better information.
Of course. I mean, I do not say that from a theoretical point of view it's hopeless. I just try to motivate that experimentally sometimes it's difficult to get out the information that you care about. But of course, there are other quantities, as you just mentioned, that are perhaps even better than just the partial structure factor, clever combination of partial structure factor, which tells you more interesting story. But this is nice for a theoretician like you, but the poor experimentalists, they have only one total structure factor. And so tell them to calculate a number structure factor. But from a theoretical point of view, you're perfectly right, of course. Okay, so now these are the structure factors. Now let's look at a different quantity, the coordination number. So if you integrate the radial distribution function from 0 up to a distance r, if you think a little bit, this gives you all the atoms that are contained in a sphere of radius r. And so if the G of r looks more or less like this is just a cartoon, and you stop your integration at this distance here, so you can estimate the number of atoms in the first nearest neighbor shell. And this quantity can, for example, be measured in NMR experiments in a bit indirect way, but some people, I trust that they actually can get out real numbers. And so this is a quantity that is integral, but it gives you some information on how the local structure or the system is organized locally. And again, just to give you an idea on how this quantity look like, here this is the probability that a silicon atom has Z other silicon atoms around it, and this is for different type of systems. So the red line here, the dots, are for SiO2. And you see that for this simple glass former, all silicon atoms have exactly 4 nearest neighbor silicon atoms. Because we have this tetrahedral local structure, and you see it here right without measuring anything complicated, that this is a tetrahedral coordinated system. Now again, so if you put in, let's say, sodium, so this is, I often use NSX for this composition here, where X is the prefactor of SiO2. So 5 means there is a lot of SiO2, and 2 means there is not that much. So these are all glasses. We are at low temperature. And you see that, for example, if you throw in 17% of sodium oxide, then immediately this network is broken up, because this shoots down, and you are forming local structure in which a silicon atom has only 3 nearest silicon atoms as neighbor. There are some that are 5-fold coordinated, etc. If you increase the sodium concentration, this whole thing shifts to the left. So you see that, so I do not want to tell the physics about this, it's just I want to show that this quantity is indeed something useful. Here it's the same thing for the same type of system, but you are looking on how many sodium atoms are around a silicon atom as a function of the composition. And you see the more that you sodium that you throw into the sample, the more is the higher is the number of sodium atom around the silicon atom.
Where is capital R in those pictures?
Nowhere. So, well, okay, because I don't show it, but so what you do is you look the G of SINA. This has a peak, a minimum, and I take the position of this minimum in order to calculate this integral. Okay? Good question, sorry about that. And I keep it fixed, and then I look at my distribution. Okay? Okay? So this is indeed a useful quantity to characterize the structure on the local level. Now, if you want to go on even a slightly larger level, then you can look at, for certain systems at least, at the so-called ring statistics. So again, you use the G of R to define what is a nearest neighbor. So nearest neighbor is the location, or all the atoms that have a distance from the atom that is sitting at the origin that is smaller than the location of this first minimum here. And so if you have a network-forming system like silica or sodium silicate, then, well, this is just a cartoon, but basically you have, let's say here in pink, the silicon atom, and in light blue the oxygen atoms, and basically you can make this loop-like structure. So a loop is you start at one silicon atom, and you take one of the bonds to oxygen, and which is attached to a silicon, and you take another random oxygen, and then until you come back. And the loop, the shortest loop that brings you back here to the same silicon atom, this is called the size of the corresponding ring. Okay. Of course, if you start here, you can do wild things. You have an infinity of loops. But the interesting thing is what are the statistics of the shortest loops. So here you have a loop, here you have a loop, here you have a loop. And the number of this ring statistic, the length of the loop is just the number of silicon atoms that you find in this loop here. And so what you can do is to look at the statistics of these rings. This is a rather theoretical quantity because in experiments you cannot study it directly, to my knowledge, but in order to compare samples that have different histories or different potentials within simulation, it's useful to look at this quantity because it gives you information that goes beyond the nearest neighbor. Okay? Now this is the statics, and now let's turn me to the dynamics. The simplest quantity to investigate is probably the mean square displacement, which is defined this way. So you look how far did a given atom go squared within a time lag t, and you take the thermal average of this, and therefore the left-hand side does not depend on the tagged atom anymore. Yes?
The previous slide, I just want to understand better, at least in 2D, that picture that we have, if I sit at one of the atoms, there's a finite number of rings.
Yes, correct.
So are you saying that it's actually difficult to calculate all the ring sizes, or is it not useful, or?
It's not useful. Look, so you sit on this silicon atom, it's attached to 4 oxygen atoms. So the rule of the game is you take, so I'm the silicon, you have oxygen, oxygen, and so what is the shortest path that you start here, and you come back? What is the shortest path? And that's what is the size of the ring associated with the silicon atom and these 2 oxygen. It will be different if I take 2 other pairs. Now, it's not very useful, for example, to look at all of the rings, because I can start here, and then instead of making this loop, I can branch off here, do something, come back here, and then do that. And it's an infinity of things, which it's not useful. Well, I think it's not useful. Perhaps it is useful, but I do not know of anybody who has ever done it. So probably it's not useful.
So for each atom, you're taking each of the branches?
Yeah. Yeah. Okay. So dynamics. So what's happening? So this is again a simple liquid. So let's start at high temperature. Reduced units, this means 5. It's the red curve here. So if you are at short times, the mean square displacement is proportional to t square, because basically this is a Newtonian dynamics, and so the displacement is linear in time, and if you square it there, it's quadratic in time. So this is log, and therefore you have a straight line with a slope 2. Now, once the particles see each other, so it's not a linear ballistic dynamics anymore. They start to collide with the other particles, and therefore it becomes diffusive. So the mean square displacement is linear to the time, and that's why you get a power law here, straight line, which means it's a straight line with slope 1. Now, if you decrease temperature, at low short times, you have exactly the same behavior, because at short times the particle does not know is it hot or cold, so it's just flying ballistically. But then it starts to see its neighbors, and these neighbors are mean they cage it. So the poor red particle is not able to leave this cage, and therefore it starts rattling around, and this is called the cage effect. Okay, so that's why the mean displacement is not increasing anymore with time. So there is this plateau region here, and it's only after quite some time that finally the particle finds a way out of this cage, and then it starts to become diffusive again. So that's the typical behavior at high and at low temperature that you find for a simple liquid. Okay? Now, what happens if you take not a simple glass form, but a network glass form? So this is, again, a computer simulation of SiO2. At short time, you have exactly the same behavior. Independent of temperature, you have a behavior that is proportional to T square. At high temperature, it's proportional to T. And at low temperature, however, at very long times, it's, again, diffusive, that is to say linear in time. But instead of having just a boring plateau, as in the simple liquid, you have here all this structure. And this structure here extends about over 1 decade in time. And so what is happening here is that since this is a network-forming structure, the particle is flying here, and then it's sitting in this network, and it starts to wobble around in a very complicated way. And so these are the phonons that you are seeing here, because these are picosecond timescales, or tenths of a picosecond timescales. And this overshoot here, for example, this is the fingerprint of the boson peak that was mentioned yesterday. It's a low-frequency harmonic oscillation of the structure that you also can see in the mean square displacement, and not just if you are looking at the density of states. From the density of states, for example, you would be able to calculate analytically, I mean, with a computer, but in principle it's an exact expression, the behavior of the system up to this plateau here, that is to say, you would be able to calculate all these bumps, etc. It's the same type of information, because up to this time scale here, on the blue line here, the system does not know that actually it can flow if it's enough patient. Okay, yes?
In this context, can you make a distinction between what you call phonons, oscillations that are being phonons, and the boson peak that you talked about? Because in principle, they're not the same thing.
Yes, of course.
And,
No, I don't agree. I mean, what do you call phonon? A phonon is, for me, a harmonic oscillation at low temperature.
right, but when you're looking at a liquid, that concept doesn't apply in a straightforward way.
Yeah, but
So,
a cold liquid at short times is a solid.
this is short enough, is the question.
Here it's short enough. You go on the tower in the swimming pool 10 meters high, and you jump into the water, it's pretty hot.
Well, it's a question of lifetime and correlation, like in terms of frequency. At low frequency, you have a very coherent frequency, and at high frequency, it's incoherent.
No, then why was Gilles yesterday saying that nobody understands the boson peak? Because it is just
Wait. No, this is a different question. You were asking what is the exact nature of these excitations, and indeed it's not that clear. But that it is a phonon mode of some sort, this I think that there is no issue about.
sorry, just maybe terminology, but just to be clear, it's not plane waves.
Oh, no, not at all. But wait, I mean, here it's class physics. There are no plane waves except for very small wave vectors where you have acoustic modes. I mean, if I'm so I'm sorry, now I see what you're saying. Okay, it's not phonons in the sense of a crystal physics, plane waves, etc. It's harmonic oscillations.
But it's different.
Yeah.
Dispersion relation. is
Absolutely, yes.
I think it's dangerous.
Okay. Good point. So, now a little bit more information than in the mean square displacement is in a quantity that is called the Van Hove correlation function. And there are two parts of it. The first one is the self part that I'm going to discuss now, and the next slide is the collective part. So the self part of the Van Hove correlation function is the probability that if a particle at time 0 was here, what is the probability that at time t it's here, that it has been displaced by a distance r. Okay, so StatMech expression is this here. You normalize it because you have summed over all the particles. And if you are looking again at the simple liquid at high temperatures, that's what the GS of R and T looks like. Now this is R, different times. And so basically here you just have these humps. So I have to point out that what I'm plotting here is not GS, but 4 pi R squared times GS. Because this is again the phase space factor because you are averaging over all directions. Okay? If I would not throw in this factor here, this really would basically look like a Gaussian function. A Gaussian function that with a height here at the origin that goes down with time, and since it's a probability, the function becomes larger. And since you multiply it by R squared, you suppress the peak at R equals 0, and that's why you get this peak that goes up. But basically, these are just Gaussian functions. Okay? So this is at high temperature. Now, if you decrease temperature, same system, at very short times, since you have this ballistic motion, these you can show analytically, still gives rise to a Gaussian function. So this is the red curve here, which looks qualitatively very similar to this black curve on the left-hand side. But then, since the mean square displacement does not increase anymore, this means also that on average the particles are not moving larger distances. And so they are stuck at a certain type of distribution, which is the superposition of all these black lines here. And only if you wait long enough, then the distribution starts to become broader again. That is to say, the particles can access larger distances. Now, the cage effect now is nothing else than these black lines where it's very dense. That is to say, the particles are stuck. And what you see is that the typical distances over which a particle can move during this cage motion is relatively small. So the typical, for this system here, typical particle distance is 1. And here you see you're stuck about 15% of this interparticle distance. That is to say, they vibrate very little. Okay? So it's not that they're vibrating not at all, but they are not vibrating 50% of the typical distance between two particles. They're vibrating about 10-15%. So the cage is small. Now this here is for a simple glass forming system. Now if you are looking at something a little bit more fancy, so first of all, if you are looking at silica, so a network glass former, basically you get the same behavior as this, grosso modo. But if you throw in sodium in the system, now you have an ion conducting glass. That is to say, in this system here, SiO2 forms a relatively rigid matrix, and the sodium can diffuse through this matrix in a relatively quick way, much faster than the silicon and oxygen atoms. And so this here is the self part of the Van Hove function for the sodiums in NS2, sodium disilicate. And what you see is that the function here, the Van Hove function, has a very different shape than the one for the simple liquid, because here you have these bumps. And these bumps here correspond nothing else than if you would trace a attack particle, it's rattling around. So this is the first hump here, and then it's jumping to a new position. This is this hump here, rattling around again, hop. And so these successive humps that get smeared out with larger distances is nothing else than this rattling and hopping dynamics of the sodium atoms. Okay, so you see that by looking at this quantity here, you start to understand already quite a bit about the transport mechanism in the system. Okay, now this was the self part of the Van Hove function. There is also the collective function. So the collective function is that if at time 0 you have one particle here, what is the probability that at time t you have another particle here? So other particle and not distance. Okay, and so mathematically this is this expression here. If you ask the same question at time t equals 0, and you think a little bit, this function is nothing else than the g of r that we have already introduced before. So this here is just a time-dependent generalization of the radial distribution function. Now, how does this function look like? Again, for a simple liquid, so at t equals 0, so you have here this first curve here. So this is just the g of r. Now, if you let time run, so these are the successive curves, then you see that this hole here that was left because a particle at t equals 0 was sitting here is slowly filled up in a very uniform way. The peak that was formed was present because a particle was sitting here at time 0 decreases, etc. And so at very long times, the distribution becomes flat. That is to say, the system has totally lost the memory that at time 0 a particle was sitting here. Okay, so nothing glorious about this. Now, what's happening if you go to low temperatures? Same function. So you see that at t equals 0, you have here this pronounced peak. And then if you let the system run, then you see that at the beginning, this peak starts to decrease, but then it's stuck for quite some time. Because, I mean, these curves here are on a logarithmic time scale, so I didn't mention this. And so it's stuck here for quite a bit of time. That's why you have these fuzzy black lines here. And so this is, again, the cage effect. The system is quite rigid. They vibrate, the particles, but they are not really able to move, and only later on they're actually able to move. And so again, this hole here at r equals 0 is filled up, but it's filled up in a different way than it's here. Here it was filled up in a very continuous way, whereas here you have some particles, or you have here a small peak, which is due of particles that were sitting here that are jumping at the position of the particle that was sitting here, but of course that particle has to leave this place before. Okay, so you see that quite a significant difference between the distinct Van Hove function at high and at low temperatures. Now, after the real space, I want to go first of all discuss a bit more generally the time correlation function. So the generic form, not the universal, but the generic form of a time correlation function of a system looks more or less like this. So this here is a time correlation function. This is an example that we will discuss in a few minutes. So, so this is the, let's say, at time equals 0, the system had a certain property. Let's say a certain density, or at this space there was a particle, etc. And you are asking what is the probability that the time t later on the particle is still sitting there, or the density of the system has this and this value. So this is a very generic expression for this behavior of this time correlation function. So typically what's happening is if you are at high temperatures, you have at short times something that is usually called a ballistic regime, that is to say a quadratic dependence of the time correlation function. This is again just because the particle are Newtonian, they displace themselves in a linear way, and so you can make a Taylor expansion of all quantities that you care about, and therefore all these quantities will have a quadratic time dependence at very short times. Then if you are at high temperature, usually you get a decay, and that is an exponential, and that is usually quite quick. It's on the order of picoseconds for an atomic system. Now if you go to low temperatures, at short times not that much happens, but then once the system starts to realize that the particles are caged, and since the particles cannot move, other time correlation functions cannot decay as well. So you see here this plateau region here, and the typical nomenclature is that this plateau region here is called the beta relaxation. Please note that beta relaxation does not mean that it's totally flat, it's just relatively flat. And at much longer times, this time correlation function decays to 0, and as Gilles was mentioning yesterday, it's no longer an exponential, but it's given by the Scholars-Williams-Watts function, which is a nice fitting function, but probably there is not much more physics in this function, but it's a very handy fitting function to describe the shape of this function. So high temperature beta is equal 1, low temperature beta is smaller than 1. And again, also already mentioned yesterday, at these intermediate times, or relatively short times, you have normally this dip that are related to this boson peak feature. Now, this here is the mean behavior of the function, because you have averaged of all the particles typically. Now, what you can do is to look at fluctuation of this function in space or in time, and that's what is then related to these dynamical heterogeneities. And there is the talk of Miyazaki and Berthier that will talk more extensively about this feature. So I'm not going to tell you anything about it. So let's now look at a few examples of this time correlation function. One that is very important is the so-called incoherent intermediate scattering function, which is defined in this way here. So again, you are looking at the displacement of a tagged particle. You multiply it with a wave vector, take exponential, etc. And so mathematically, this object here is nothing else than the space Fourier transform of the self part of the Van Hove correlation function, so of this object here. So it's just a space Fourier transform. Now, this function here can be measured by incoherent inelastic neutron scattering or X-ray scattering experiment more recently. And again, so you come in with a certain wave vector, you go out, you hit the neutron, let's say, it hits the sample, gets scattered, goes out with a certain wave vector, and also gains or loses energy. And so you have the Q is the Q that is here, and the energy loss or gain is related to the inverse, let's say, or the frequency quantity of this object here. And so once you have this function here, which I will show it later, but it has more or less this shape here, you can calculate the area under this function. This allows you to calculate or define a relaxation time tau. And again, as I mentioned, this quantity characterizes the mean behavior of the system. If you care about dynamical heterogeneity, you look at fluctuation of this quantity, and therefore there is the talk by Ludovic Berthier. So how does this function look like? Again, for a simple liquid. This is for a wave vector that is close to the peak of the static structure factor. Different temperatures. If you are at high temperature, you see you have here this ballistic regime, and then it very quickly decays to 0. So this is just an exponential. If you go to lower temperature, blue line here, then you see that you have here this plateau-like region, and then finally the alpha decay. And what I have to emphasize is that this plateau here, you see it only if you plot this function on a logarithmic time axis. If you would show it lin-lin, then basically it would look like puff, and then it comes down. Not even linearly, it's basically just a little bit fluctuating. So here it's really crucial that you are looking at this quantity, since it's classical physics, on a logarithmic time axis. Okay, so qualitatively, of course, you're right. So now this quantity depends on the wave vector, and so the general. So I don't want to go into detail, but I mean, what people care about is on how the stretching depends on the wave vector, how the relaxation time, so the area under the curve, depends on the wave vector, depends how the height of this plateau depends on the wave vector. For the self function, for example, the height here is basically a Gaussian function in Q. So it's e to the minus q squared, to a first approximation. So this is a quite good approximation. The relaxation time for the self part, again, this is basically just the hydrodynamic behavior. It goes like 1 over q squared. And the stretching is not that markedly Q dependent. So this is for the self function. For the collective function, it's much more complicated, and so. But I will discuss this a little bit later. Other question? Okay. So this is a simple glass former, and so this is silica, SiO2. It's the same type of quantity, high temperature, low temperature, and as promised, Gilles, here, the cartoon that I showed you about the boson peak, you really can see it. It's this dip. What does this dip mean? I mean, imagine that you take a very simple system, a harmonic oscillator, and you calculate this quantity. For a harmonic oscillator, it will just do this, okay? Because the particle goes back and forth, and that's what's going to happen. Now, if you take a damped harmonic oscillator, this quantity, or a harmonic oscillator with noise in it, the oscillator will dephase, and therefore, depending on how much noise you give it, you will see a few oscillations, and then it will go down to 0. And since at short times, silica is, or at low temperature, can be considered as a collection of damped harmonic oscillators, and with typical frequencies around this boson peak that are quite prominent, you see here the ghost of this damped motion, and that's why you have the dip. Okay? So if you would have enough resolution in time from the neutron scattering thing so that you actually could access this region here, then you should be able to see it. Okay, this is to say this probability that if I have at time 0 a particle here, what is the probability that at time t I have a particle over here? Now, again, this quantity here can be measured in coherent inelastic neutron or X-ray scattering experiment with exactly the same procedure, and the time comes again from the time Fourier transform of the energy transform. And so, if you, also for this object here, you can look at the fluctuations in space and time, and you get the dynamical heterogeneities. If you compare this, and we will do this in a second, compare this function with the self one, grosso modo they look similar normally, but there are surprises. Okay, so normally the typical relaxation times at a given wave vector of the Fs and the F are quite similar. I mean, I'm not talking about a factor of 2 or 3. The height of the plateau within 10-20% is the same. Stretching is quite similar. If you have understood this, very often you have understood also the other quantity, but not always. Okay, so how do these functions look like? So this is the Fs, and this is the F. Excuse me.
I don't understand. Why do you say it's on the previous slide? You say point 1 is the space Fourier transform of the distinct Banach function, but it contains both the self
Yes.
and the
True.
GD and GS.
Yes. So it's wait.
Because the indexes can be
To be frank,
I mean,
I do not. I mean, it.
it's minor.
Yes, I understand, but you're right. You got me because I do not know whether I screwed up this formula that I should put in here j not equal k. Does anyone know? Is it just the cross term or is it the whole? I forgot.
No, it's a total.
It's well,
But the Q dependence of self
they are very different. Okay.
distinct enough. So you have to make some assumptions that it's possible to separate.
Okay.
But you're right. Basically, they contain both.
Okay. Good point. Okay. So how does this function look like? So this is neutron scattering data of a metallic glass former by Meyer already quite a few years ago, but I think it's beautiful data. What he measured are the symbols, colored symbol at different temperature, and well, don't care too much about the black lines. These are fits. But you see, that's how real life in neutron scattering experiment looks like. So what you are measuring, as I mentioned, usually in neutron scattering you are not measuring in time, but in frequency, so you have a certain resolution, and the inverse of this resolution gives you the shortest time that you can measure. Then the next data point that you get is twice this time, so this is a factor of 2, then 3 times, etc. So that's why you get these points here. Okay, and but you see that's what neutron scattering is able to do. I think it's really excellent data, and but you do not get necessarily to very short times where actually would be able, let's say, to see the boson peak. I don't know, is it possible now to have good statistics at tenths of a picoseconds or something like this?
Yeah, it's a question of energy resolution also.
Yes, sure, but
incoming energy. So with pulsed neutron, we can improve.
okay. So
we are in the process.
okay, good. So sooner or later you will see the dip of the boson peak in real experiment. So now, as I said before, usually coherent and incoherent functions are basically the same or very similar, but there are surprises. If you compare these two expressions here, and if you go to very large wave vector, Q, this means that the only term that will survive here, so if Q is very large, and you know that Rj minus Rk, this cannot become for finite time or for relatively short time, it cannot become very small because the particles have, at time equals 0, they have a certain distance, and so at short times this distance still is finite. If you multiply something finite by a Q vector that is very large, this becomes huge. And exponential of very huge is something random, I mean, if you have the I there, and therefore these functions decay very quickly to 0. And the only thing that survives is the diagonal term, j equals k. That is to say, you see it directly that for large wave vector, the collective and the self, they become identical. Okay? And this here, this result, trivial mathematical result, you see directly here in the sodium silicate system. So in red, it's the collective. In blue, it's the self. Different wave vectors. This is a relatively large wave vectors, and you see the two functions are indeed quite similar. However, if you go at smaller distances, that is to say smaller wave larger distances, excuse me, but that is to say smaller wave vector, then you see that this difference can be orders of magnitude, and in these ion-conducting glass formers, for example, the self and collective functions behave in a very, very different ways. Again, I don't want to go into the details, but just want to convince you these functions are interesting, and especially for glass physics, they really can teach you something about the mechanism of the transport of the system. Okay. Now, this was space and time, but already Gilles mentioned it yesterday, and so I will be rather brief on this, that many experimental techniques, they are not measuring only in time, but in frequency. So what you can do is you take your time correlation function, take a time Fourier transform of this correlation function. So there are certain type of experiments where you measure this, or where you measure the so-called generalized susceptibilities, and you have this fluctuation dissipation theorem that relates the response or the susceptibility to omega times the imaginary part of the Fourier transform of the time correlation function.
Sorry, Walter.
Yes.
Technically, if this is truly the Fourier transform, the full Fourier transform, phi of omega is real.
Okay.
It's only if you take the Laplace Fourier transform that you have a real and imaginary part. So just to mention that it's not the same formula that I had because I had the full Fourier transform. It's just not to confuse the audience.
And may I said, thank you very much. You're right.
I'm not sure that everybody heard what
Huh?
I'm not sure that everybody heard what Gilles said.
Okay. He said it's wrong. No. Yes. He's polite. No, he said that it's not the Fourier, but the Laplace transform, and you have to be careful about this. And he is right, of course. So, sorry about this. But note, this relation here is only valid if you are in thermal equilibrium. It's an exact relation, but only in thermal equilibrium. Now, just as a glimpse into the future, what you're going to hear about it. So if you're out of equilibrium, say in the glass, you still can measure this, you can measure this, and see how these two quantities are related. And then you have this factor here, which is no longer really temperature because you're out of equilibrium. And you will see the talks by Kurtjan and Franz that will tell you all the glory story about these relations and how, no? You should. Well, okay, so I hope that Jorge will do so. And how you can measure these effective temperatures, etc. Now, again, Gilles showed this yesterday very briefly, so it's the same thing. So if you have something like this in time, you get something like this in frequency. And so basically, the people that measure in frequency in their head, they have their particular chip to make this analogy that this peak corresponds to this peak corresponds to this, and they are able to discuss the various peaks and how they move, etc. So for many quantities, this is interesting. For many situations, sorry. And also this picture, these are the results by Lunkenheim et al. Dielectric measurements, marvelous 17 decades in frequency dielectric measurements. The problem is it's not that clear what you're actually measuring on a microscopic level, but at least the temperature depends of the peaks, etc. This you can pull out, and it gives you interesting physics. Okay, 4 more slides. Everything that I told you so far, this was about Newtonian dynamics. But there are important class of systems that are, it's the system, the particles are not moving according to Newtonian dynamics, but Brownian dynamics, and Francesco Shortino will tell you a lot about gels. That's the typical situation where you have no longer Newtonian dynamics. And so if you, Newtonian dynamics is if you have that mass times acceleration is given by the force here, and so then the right-hand side, this is 0. If you have Brownian dynamics, you have here this equation, but no inertia term anymore, and where you have here friction zeta that is proportional to the velocity of the particle, and you also have noise that with average of 0, and that is usually delta correlated in time and in the coordinates in the particles. And what you can do is you look at how does a particle or a system in which the particle move according to this dynamics compare, for example, with the Newtonian dynamics. Is it very different, yes or no? And so just in order to give you an example on what is different and not, so this is again from a computer simulation, this is the self-intermediate scattering function at different temperature. So I already showed you the red lines. This is the Newtonian dynamics at high and at low temperature, so exponential decay, and here plateau and stretched exponential decay. If you look at the relaxation dynamics with such a dynamics here with a certain friction coefficient, then you see that at high temperature, again, you find basically an exponential decay. And at low temperature, you see, again, this plateau and the stretched exponential decay. What is interesting is that the shape of the curve at low temperature is independent of the microscopic dynamics. That is to say, the stretching, that is to say, the way how the particle leaves the cage seems to be independent of the microscopic dynamics. That is to say, from this point of view, it's the same type of physics, but you are looking at Brownian dynamics or Newtonian dynamics. As long as you care about the alpha relaxation, all the short-time dynamics here are, of course, very, very different. Yes?
I'm a bit confused. When you talk about this, do you mean that you replace the effect of the neighboring particles by your noise term? Is that what you mean?
No. It's really, so Newtonian dynamics you understand, and I do a completely new simulation with this dynamics here. So that is to say, the particles, they see the forces, a given particle sees the forces, the deterministic force of the other particles, but also it sees a friction term and a white noise term.
Yeah, but the friction term and the white noise term, they usually
True.
And so is your path, in your previous slides, you talked about just the particles.
Mhm.
So I
Okay.
assume that they
Okay,
know
okay.
this.
So what you should imagine, so I see your point, you're right. So before I had atoms. Now I have colloidal particles that are sitting in a bath, technically. That's what I want to simulate. Now, I'm too poor to simulate the particles of the bath, so I still sit only with the big colloidal particles. That's the left-hand side. And I take a poor man's solution of the bath that I randomly bump into the particles. Okay.
So I think the noise and the damping, they really do represent
A bath.
the
Well, it's not the other colloidal particles, it's the particles of the bath. Which I do not, and the bath I do not simulate.
Sure. You just assume this correlation.
Exactly.
But really, they represent the effect of the surrounding medium.
Exactly. Okay, good.
You say it's much slower, Brownian dynamics.
Yes.
But is the temperature, if you plot the relaxation time with respect to temperature, do you get the same temperature
Yes.
dependence?
Yes. You have here a factor of, I don't know, 30, but the factor is constant.
It's constant. Yes.
Exactly. Yeah.
Just to understand, the Newton dynamics is with m different from 0 and zeta equal to 0, and the Brownian dynamics is zeta different from 0 and m equal to 0 or m different from 0. So
Okay.
compare the two.
So, yes. Okay. So, I'm cheating. So, Newtonian dynamics is, as you said, m is 1, and zeta equal to 0, and therefore also the noise is 0. Brownian dynamics, the real Brownian dynamics is really or pretty hard to simulate in a correct way. So, what we did was to say, well, what we are doing is we keep this inertia term here, but we look at a very strong friction. And this gives the same, and we did some preliminary simulation in order to see this gives the same behavior as the Brownian dynamics. So we cheated a little bit, but not much. And the cheating is under control. It's a stupid, the numerical algorithms that you use to solve this equation are very efficient. If you have not the second order equations, they do not work anymore. And in fact, it's quite, this was done already quite a few years ago. What I would do these days, I would just do Monte Carlo, and I would get the same result probably. But if you really want to do Brownian dynamics with all this stuff here, it's still pretty hard. There are no good algorithms. Because the result depends on your step size that you're using. You have to look that you have sufficiently small step sizes, and they become very small before you have converged. It's a stupid algorithmic problem. There's 3 more slides. Depends on how you want to do.
Since you're continuing, I guess it's fine.
It's up to you. I'm not falling asleep, but
There are reasons that
okay.
So if the noise and damping represent the effect of the surrounding particles, then what does D represent? It's sort of the average part of the...
This here?
Yeah.
It's the deterministic interaction. These are Lennard-Jones particles. So it's really, it's not hard spheres. We didn't care about the hard sphere at that time, but it's really Lennard-Jones particles. Therefore, this is R to the minus 12 minus blah, blah, blah. It's really the interaction between particle, deterministic interaction between particle number I and J. Okay, yes? There? S, stochastic dynamics. So this is, you're right, sorry. So Newtonian dynamics, Brownian dynamics, stochastic dynamics, and stochastic dynamics you can move it around by means of this friction constant. is if theta is equal to 0, you get the Newtonian dynamics, and if it's very, very large, you get the Brownian dynamics. So it's basically our cursor to say where we are. Okay? Now, the last few slides are on transport quantities. All of you, I suppose, know that the famous Einstein relation between the mean square displacement and the diffusion constant. If you know the mean square displacement at long times, you get the diffusion constant. Fine. Also, especially of interest is the viscosity, and there is the expression that if you calculate this somewhat obscure and funny quantity here, you can obtain directly the viscosity, and therefore analytically or within a simulation you have access to this quantity. So that's really the viscous flow of your sample. And already yesterday it was mentioned that we have the Stokes-Einstein relation that relates the diffusion constant with the viscosity. But please recall, this holds for a big sphere in a medium. And so this does not necessarily apply to spheres that are the size of a molecular system. Yes?
Yeah, just in correction, some people have started calling this relation Stokes-Einstein-Sutherland.
Okay. Okay.
Sutherland did it a year before.
Yeah. Okay.
So in some, I see some paper where A alpha beta has plus minus sign. There's some confusion about it. Can you just verify?
Here?
A alpha beta, it's less than A alpha beta. Next.
Ah, here? No, this one.
Yeah.
OFA. No, I think. Let's discuss this later. This is very technical. Okay. So this is important. So, however, people look at this relation because you can measure with certain experimental techniques the diffusion constant, of course, also the viscosity, and see does it break down, yes or no. And yesterday we heard that something is happening. Now, the last thing is most of the stuff that we care about, these are not atoms, it's molecules. And molecules, they have orientation degrees of freedom. They are objects, no longer points. And so if you let uj sub j be a vector that is fixed in the molecules, and therefore what you can do is to define a rotational correlation function in this way. So what you do is to correlate ui of the ith molecule at time t with the orientation of the jth molecule at time 0. And instead of looking just at this function object here, what you do is to look at this number, calculate the Legendre polynomial of order L, and take the thermal average. Okay? And this gives you this CL. And one can show that if you are doing a dielectric experiment, the important quantity is L equal 1, whereas if you are doing light scattering experiments, it's L equal 2. Thus both techniques, experimental techniques, probe the reorientation motion of the molecules, but weighted in a different way because you're looking at different Legendre polynomial. This quantity here, this time correlation function, can be generalized in various ways. First of all, you can just look at the self part. This contains also interesting information. You can look at the wave vector dependent and not just look at any two particles. And again, from this quantity here, you can extract a relaxation time, and there is some sort of a generalization of the Stokes-Einstein relation, which is the Debye-Stokes-Einstein relation between the rotational diffusion constant, how does a sphere to which you have attached this vector reorient itself in a viscous medium, and so you can talk not only on the breakdown of the Stokes-Einstein relation, but also of the Debye-Stokes-Einstein relation. Summary, I hope to have convinced you that, so I have introduced various structural quantities, I don't want to repeat them anymore, dynamic quantities, there are many, many more If you have a system that is a bit more complex, usually you have to think a little bit, how can I characterize it? But this is the zeroth order knowledge that you have to do in order to characterize the structure and the dynamics of a liquid, and therefore also of many glass-forming systems. So for this, I would like to stop.
While finding the relaxation time from the FSKT or FKT, what Q I should take, the first peak of this?
Into three pieces, and the same thing happens at different wave vectors. It strongly depends on what wave vector you are looking at. So you have to look at all of them. If you have only one experiment, take the maximum.